pointer?
Yes, I do. Yeah, fantastic. Thank you very much. Okay. Thank you very much for the invitation. It's really a great honor to be here to talk to you guys. I'm really passionate about this stuff. It's really a great opportunity to share some of this enthusiasm that I have with about this stuff with more enthusiasts. So, as Linda mentioned, so I'll talk a little bit about dark matter and gravitational lensing and submillimeter astronomy, radio astronomy, ALMA. So there's a lot of different concepts, and so we'll try to go through a lot of these different things. Please don't hesitate to interrupt me at any point if you have any questions. If anything is not clear, I'll be happy to stop and clarify it. So some of the stuff that I'll be talking about is about the discovery of a dark matter dwarf galaxy. So some of you might have seen some of this in the media that was covered recently. And if you haven't, we're going to go through all the details of this and get to that. In science, we rarely work alone. So there's a lot of people that I've had the privilege of working with. So I would just like to acknowledge them here. And so a lot of the work that I'll be discussing has been made possible by the contributions of these people. And I'm also going to try to add some of my personal history of how I got to be doing this, what I'm doing, and how my research evolved and I got to the point where I am and discussing the things that I'm discussing today. So let's start here. So about 10 years ago, that's where the story begins. I was an undergrad student at the University of Victoria in Canada, and I was just finishing my undergrad degree, and to tell you the truth, I was like one of the worst undergrad students ever. I was definitely the worst of my year, just trying to pass the courses and do the minimum amount of work and just get out of there. And somehow towards the end of it, I thought, maybe I like astronomy too much. Maybe I don't want to leave it. So this is the campus of University of Victoria, and it used to be famous for its unlimited supply of bunnies. So what you see here, that's the library, and there were bunnies everywhere. And now I've heard that they have completely disappeared. And I'm not allowed to say what happened to them. So this is a beautiful campus. So, on the other side, that's Seattle. And this is Victoria. And so I thought it would be great to go to grad school and do more astronomy. And but it's competitive. You need great GPA. You need to have good letters of reference, some experience working for a professor or something like that, doing some research. I had none of those. I had my enthusiasm, so I thought maybe that's going to push it. So I looked around a little bit, and I came across the website of a professor at McGill University, and accidentally I came across this thing that I found this line on his website that said, I'm interested in gravitational lensing, and if I could just read it here. So it seems clear that strong lensing needs to be studied in much more detail using n-body simulations. I didn't understand what exactly he wanted to do, but I thought this is somebody who was hiring. So, it looks like an open invitation for some grad student to apply. So I thought, I'm going to do that. So I sent him a desperate email, and I said, yeah, well, of course. I'm interested in strong lensing, and that's how I ended up, spending the next 10 years of my life studying, how images are squeezed and stretched. That's basically it. So at the time, what I knew about gravitational lensing came from these beautiful images of Hubble Space Telescope. So many of you might have seen these. You have these clusters of galaxies that are groups of hundreds to thousands of galaxies that are just bundled up together. And they're held together using gravity. And the gravity is in fact so strong that they distort the images of background galaxies. So these are galaxies that are behind this main cluster, so what you see here in orange, for example, and their image is being stretched because gravity is bending the light. It's really fascinating to see that gravity, that everyday life you're just used to it, objects drop, is doing something so fascinating. It's changing the appearance of things, making them distorted, making them have multiple images. So for example, here you see one image, and then it's the same image of the same galaxy that you see here, the same color. Here's another image of a strong gravitational lens. So you have the cluster, lots of galaxies there, and then you have the lensed arcs of the background galaxies. These are galaxies that are much farther away. It was pretty amazing. So I thought this is a really amazing phenomena to study. So let's just see how lensing actually happens. So imagine that we are on the Earth here. We are on the left side of this little animation. And there is a galaxy that's perhaps a cluster or something like that, the blue galaxy. And there is another galaxy that is right behind that one. And that's the red galaxy that we see here. So as the light rays of that red galaxy, they travel and they just pass near this one. They get bent because of gravity. So when they come to us, they come from different angles. So they come from different orientations to us. And as a result, here on the Earth, when we look at it, we see multiple images. So we see a ring-like thing. So we see one image here, one image there, something like that. It's just because the light is being bent and coming to us from different directions. It's a little bit like looking at images of fish in a fish tank. So if you ever look at the corner of a fish tank, you'll notice that sometimes you see two images of the same fish. And I have one of our favorite pets demonstrate this, Mr. Mango. So as he just goes to the corner, you'll see that you see two images, and it's the same fish. And so the reason for that is that the light rays are just coming to the two sides, and here, because of refraction, getting bent and coming to our eyes. So we see the same phenomena in the sky. So look at this. This is a galaxy here, lensing the image of a background quasar, and you see two images of the same quasar, very similar to the same thing. Now, the difference here is that when it happens in the sky, gravitational lensing, first of all, the bending of light is because of gravity, not because of refraction, as is the case in a fish tank. And the second thing is that gravitational lenses like this one usually are circular. They're not like a fish tank, they don't have just straight sides. So images look distorted like an arc. They look circular. But there is a way at home that you can simulate the effect of a gravitational lens, and that's using a wine glass. So because wine glass, the foot of a wine glass is round, it can produce images that are very similar to images of gravitational lenses. So I've nominated another one of our favorite pets to demonstrate this with this video. And so what you need is first, there you go, a wine glass. And you also need a candle to show the effect. And it helps if you've had a little bit of wine and maybe somebody to accompany you for the experiment. And so if you just turn off the light and bring the wine glass in front of your eyes, that's spark. And so bring it in front of your eyes, you start seeing that the image of the background candle, it becomes into this circular ring around the foot of the wine glass. It's very similar to exactly what gravitational lenses in the sky they do. So they produce these ring-shaped things that we call Einstein rings. So sometimes, depending on where you put the wine glass, they could form 2 images or 4 images or a full ring, and that depends on the configuration that we have. So in this analogy, basically the wine glass is the middle galaxy, what we call the lens galaxy. And the candle is the background galaxy, who's just much farther away. Its light is being bent by the middle galaxy. Now, the key idea here that you have to keep in mind is that the wine glass, if I cannot see it, it doesn't matter. I know it's there, and I can measure something about it and maybe learn something about its shape just by the way that it's distorting the light of the background candle. And that's a very key, important idea for gravitational lensing. So, and hopefully once you're done, your buddy didn't find that you're a nerd and didn't leave you, so Spark's still sitting there. So that's an image of gravitational lens in the sky. It's absolutely fascinating. It's really fascinating to see something like that that background galaxy doesn't look like that. But, we see it as this beautiful, almost full arc, full circle around the middle galaxy that is doing the lensing. So just like in the case of lensing with your wine glass, you need an almost perfect alignment of the wine glass and the background candle with your eyes. For gravitational lenses, too, you need an almost perfect alignment of the 2 galaxies with us. So one galaxy has to be almost perfectly behind the other one for this effect to work. Otherwise, it's really not a strong thing. And so because of that, finding gravitational lenses, strong gravitational lenses, is very difficult. It's a very rare phenomena. And until recently, we only knew of about 100, 150 gravitational lenses altogether. So part of the talk, that I'll be going through is how to discover new gravitational lenses and what techniques do we use. So being interested in this got me into grad school in Montreal. That's a sunny, beautiful day in Montreal. And it was exciting. That's the campus of McGill. And so while I started to learn about the basics of gravitational lensing, I spent a few years being completely confused. What was going on? I was interested in lensing, and I knew that it's bending of light, but what was the context? Why study gravitational lensing at this particular time? It's been discovered for centuries, well, decades. What exactly were we trying to do? I really didn't understand for quite a few years. And so I just kept on, studying whatever I could and learn. And soon I started realizing that, through my PhD advisor, I was a part of the South Pole Telescope collaboration. So that's the South Pole Telescope. As the name suggests, it's in the middle of the South Pole. And the South Pole Telescope had just discovered a few hundred extremely bright galaxies. That's all we knew about them at the time. So there were a few hundred very, very bright galaxies that were exceptionally bright, that we didn't expect to be that bright. And so that was the subject of my study. So this is also the South Pole Telescope, and it observed the sky in a millimeter wavelength. So, wavelength of light that is about 1 millimeter. And yet another image of the beautiful South Pole Telescope. So this is one of the South Pole Telescope maps. So this is what it observes in the sky. So the fluctuations that you see here are the cosmic microwave background, and that's the main science of the South Pole Telescope. I'll mention that in a little bit. But let's focus on these points that you see, right? These points are some of the points that the South Pole Telescope had discovered. Things that we see as just a very bright blob, but we couldn't really resolve to see what exactly they were. So the idea was that, the question that my PhD advisor had was, is it possible that these very bright things that the South Pole Telescope sees are in fact gravitationally lensed galaxies? And so if we could just zoom in on one of these things and see it with better resolution, is it possible that there is a galaxy lensing the light of a background galaxy, something like that? And so now you might ask yourself, why would a gravitational lens, something like that beautiful with multiple images and arcs that we dock, would just appear as like a blob? And the answer to that is resolution. Of course, if you have very, strong glasses, just take off your glasses, everything looks like that. So, the cars in the back might have, 2 headlights, but you see as 1. So when you don't have enough resolution, everything looks like a blob. So it's possible that we don't see these different images because the telescope doesn't have enough resolution, so everything is just a giant blur. So this is a simulated image. So imagine that this is an unlensed image. This is a lens, so now you can see, okay, there is one image here and an arc on the other side. That's a gravitational lens galaxy. Now I look at it with a telescope that doesn't have enough resolution, and I see both of them as blobs because I don't have resolution. But if you notice, the lens galaxy is a lot brighter. And the reason for that is that gravitational lensing also magnifies, it amplifies the amount of light that comes from these galaxies to us. It focuses the light of these galaxies to us. So it makes anything that is being lensed, even if you cannot resolve it, even if you cannot see structure, just the light that is coming is a lot brighter. So it's a little bit like burning a poor ant with your magnifying glass, right? The poor ant sees the sun a lot brighter than what it actually is. And so, that's why it burns. And so gravitational lenses are also like focusing the light of these distant galaxies onto us, but, fortunately, the decision is less fatal here for us. So I spent the next 4 years studying computer models of gravitational lensing and the statistics of gravitational lensing. So what we were doing was produce these model simulations of the universe where we have a population of background galaxies, a population of foreground galaxies, and study what is the chance probability that some of these galaxies would be right behind the other ones. How bright would the background be? How many times would it get amplified because of lensing? And then study, would it make sense that we would have a couple of hundred of these extremely bright sources in the sky? Right, so we had specific measurements about these things. We didn't know if they were lenses or not. We speculated they might be gravitational lenses, but we could measure how bright they were, for example, at a particular wavelength. So we had some models, and from the models, it seemed that it was plausible and strongly plausible that these were gravitational lenses, simply because we don't expect to have so many bright galaxies if there are not lenses at all. So, we don't expect to have galaxies that are that extreme and exceptionally bright by themselves in the sky. So if they happen to be that bright, it's just suggesting that something else is making them, brighter than they truly are. So now at this point, you might ask yourself, why spend years studying this thing when you can just look at them with a bigger telescope, right? I mean, all I need to do is just get a more powerful telescope, look at them and see if they're actually strong lenses, if they have multiple images or not. And the answer to that is, well, first of all, that's exactly what I thought the whole 4 years. It's like, why am I doing this when somebody can look at them? But the truth is that telescope time is very expensive. A big telescope, could be hundreds of thousands of dollars for a few hours. That's, just the cost of operation and cost of building a telescope. So if you're going to ask a giant telescope to look at your sources, you really need to build a very strong case why you think this is a good idea to dedicate, prime telescope time to look at these sources for whatever case. So you need to study from every different aspect, every different angle, and make a convincing case that it's worth it to spend this time on the telescope. And the second thing is that there was no such telescope at the time. So we needed a big telescope to look at these sources in millimeter and submillimeter bands, and at the time we didn't have that. So we definitely needed a bigger telescope. We were lucky, though. We were really lucky, because situations like this in science, sometimes you need to wait years, sometimes decades, for the situation to advance a little bit, for things to change. But in this case, in 2011, just before I started wrapping up my PhD thesis, the Atacama millimeter submillimeter array in Chile started operating. So the telescope, for short, is called ALMA. It looks at the sky in the wavelength of light that is about, a millimeter or shorter, submillimeter, that's what it is. And here's a little video of the construction of ALMA when they were building it. So you can see this little telescope. This is one of the antennas going uphill. It looks like a little snail. And so there are 66 dishes. And they all move to this high side, which is 5,000 meters high. Very little oxygen there. And there's very, very little humidity. And ALMA is a huge international collaboration that cost nearly $2 billion to build over a few decades of design and 10 years of construction. And so here you see its operation. So these telescopes, they work together. They combine their images together. The magic of ALMA is that you get the image of these individual telescopes and pass them down to a supercomputer and combine them together. And the image that you make out of that is as if you had a telescope that was as big as the distance between the different antennas. So here is another picture of ALMA, and here's the supercomputer. It's called the correlator. So the technique is called interferometry. What you do is that I put two antennas some distance apart, combine their images, and now I have a telescope with a resolution that is as big as if I had a telescope that was as wide as the distance between them. So we can put these telescopes as far as 10 miles apart. So effectively now, instead of a telescope that is 5 meters or 10 meters wide, we have a telescope that is 10 miles wide. And that's the kind of resolution we can get out of it. It's an extremely powerful technique and really fascinating. So here's one of the antennas being on one of these special trucks that move them around. And so you can move the telescopes around throughout the whole year, put them in different configurations. And they do that very regularly. So throughout the year, you look to different configurations where you put the telescope progressively at longer and longer distances from each other. And you can get higher and higher resolution depending on what science you want to do. So in 2011, while it was still incomplete and only with a fraction of its antennas, so the total number of antennas is 66, but at the time it had only about 15. So ALMA announced that they were going to look at basically early science, so use the telescope to test its capabilities for some science. So there was a call for proposal for scientists around the world to submit their proposals to what to use ALMA for. And so our team definitely wanted to do the same thing. So all of a sudden, all these studies that I had done for years to see if these population of population of bright galaxies were strong gravitational lenses or not, well, all of a sudden was at the center of this decision. Can we use ALMA to look at these sources to confirm for sure that they're absolute gravitational lenses or rule them out? So we had a proposal we submitted, and we were really lucky. So we were one of the few groups that were assigned a high priority to look at our targets with ALMA. It was really, really exciting. So this was around, if I go back, this was around October 2011, and I had a few months to just worry now. Because, it looks like there's a propaganda and you convince people, no, this is what we should do. And then you wait and ask yourself, is it really true? Or did I make a mistake in my code? When you see how the sausage is made, you worry about it a lot. And what if one of these assumptions was wrong? And I don't want a lot of people to be mad at me, what happened. So there's some tension at times. Finally, in February, we got the data we were waiting for. And I thought they were absolutely beautiful. Almost every one of these bright sources happened to be gravitational lens. And honestly, I was absolutely amazed by this, because I thought, how is it possible that science actually works? I thought I was making a lot of this stuff up somehow, because we have so many assumptions, if this and that and that and that, but somehow you just get confirmed by your observations that it seems to work. So what you see here are in blue the lensing galaxies, so in the middle, that's images from Hubble Space Telescope. And in red, you see the observations of ALMA from the background source. So these are in two different wavelengths, two different frequencies, complementary to each other. So if you just look at them with Hubble Space Telescope, you don't see it because the background sources only emit light in these wavelengths. And so it was really, really exciting. One of the most important conclusions here was that we found a very cheap way to find gravitational lenses, right? Just look at the brightest sources in the sky and their lenses. That's pretty easy, right? Because the brightest sources are just bright because they're lensed. So we published this work in 3 different articles, and it made a big splash that got a lot of media attention. And it was really exciting to see that just, the first observations of this amazing telescope, ALMA, had produced such amazing science, and lots more to come. Made it to the Big Bang Theory on the board, and we were excited about that. That's basically the 3 images, one of the sources here. So this is some of the travels that I did in the last couple of years of this work when I was doing a PhD. Lots of traveling. We have these collaborations that are all over the world. I think I just lived on a plane all the time. I always called myself internationally homeless at the time. And it was really exciting. So this desperate attempt to get into any grad school to do something had somehow ended up being super exciting discovery, and it was really great. And luck is a huge important factor. Being lucky is definitely in science an important thing, but I think more important is to work with people who know better than you. And so I was lucky on both counts. So it made me climb onto these giant telescopes, and I came to Stanford after that, and I found an astrophysicist's wife, which was also great. So win, 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 win. So next. So when I came here, I thought, so we have all these gravitational lenses. What are we going to do with them? What are we going to learn from them? It's kind of exciting to just find them. But once you find them, what do you do with them? We are always looking for some new interesting science to learn. And after a little bit searching around, I realized that what would be really exciting with these things is to use them to map the clumpiness of dark matter. So the dark matter halos of galaxy, how clumpy are they? Are they like in this image, have a lot of structure in them, or are they smooth? So I'm going to come back to this in a little bit and explain why it's interesting and why it's important and why we're trying to do or how we're going to do. So, but right now I'm going to step back a little bit and talk about dark matter itself. What it is, what we think it is, and what we know or don't know about it. So the story of dark matter starts in 1930s.
Is that a real picture that you just showed, or is it?
No, this one is made up. This one is made up. Yeah, this is made up. Yeah. So the idea here is that I think this is an image of an actual galaxy. But what you see here comes from computer models of dark matter. So we don't see dark matter at all, and I'll come to that. So this is at least the blue stuff is computer model. So in 1930s, an astrophysicist called Fritz Zwicky at Caltech, he did something nobody else had done before. He looked at clusters of galaxies, like this one. This is also a simulation, computer model. And so he looked at how fast individual galaxies were moving around in these clusters. So clusters, if you remember I mentioned earlier, that are these groups of hundreds and thousands of galaxies that are being held together because of the gravity of the cluster. And so these galaxies individually, they move around, and they move quite fast. So the cluster needs to exert some force on them to prevent them from just flying away. And the faster they move, the more gravity you need to just be able to hold them together, right? And so if you don't do that, then the galaxies, they would just fly apart, and a cluster will never even form for us to see it. So if the cluster is there and things are moving, there must be some gravity to balance that their inertia that's just trying to go out. So by measuring the velocity of these individual galaxies, what you can do is then measure how much gravity is needed to hold them together, to hold the cluster together. And so that could be used as a way to measure the amount of matter in a cluster. So and that's what Fritz Zwicky did. And to his astonishment, he found that these galaxies were traveling way too fast. So in fact, so fast that when he calculated, he realized that there was 5 times more matter from his calculation in the cluster than all the regular matter that he could see, through his telescope, through stars and things like that. So the galaxy, whatever he could actually see. And so that's what we call dark matter. This is matter that has gravity, but we can't see it for some reason. A few decades later, in 1970s, Vera Rubin, she studied the rotation curves of spiral galaxies. So she studied how fast stars in the spiral galaxies are just rotating around the center. And what she also discovered was that in the outskirts of galaxies, things were spinning and rotating way too fast. And her observation pointed out to the existence of about the same amount of dark matter as what Fritz Zwicky had come up with. So she explained that if there was some amount of matter that we can see in the galaxies, it would basically make these stars go faster in their outskirts. And so at the time, this was the strongest evidence for the existence of dark matter at that point. So ever since then, a lot of different observations have come to the very same conclusion, that our universe seems to have this mysterious matter in it that has gravity, and it permeates our universe everywhere, but it cannot be seen. So we can see its effect on galaxies, on clusters of galaxies, and everywhere in between. But we cannot see it directly, but we can see its presence through the gravity that it exerts on all these different astrophysical objects. It's amazing that all of these different studies with very different measurements at different scales in the universe arrive at the same conclusion with the same amount of dark matter too. And that's really fascinating. So that has convinced a lot of astrophysicists that dark matter is basically a sort of particle that permeates our universe everywhere. So I guess there are some other different theories out there. So the million-dollar question here is that what is exactly the cause of this dark matter? So our current best theory for this is that it must be a kind of particle, something like protons or neutrons or electrons are particles. So it's a similar particle that is all around us, except that it doesn't interact with light, and because of that, it's completely invisible, and basically it's transparent. And our current best guess for what kind of particle it is, it's called the cold dark matter. And so, and I'm going to refer to it as the CDM, or the cold dark matter, throughout my talk. I'm going to come to it a little bit later and discuss what exactly cold means here and why we're interested in that. One of the places where we see the influence of dark matter is on the cosmic microwave background that I mentioned earlier. So this is the Planck satellite looking at the cosmic microwave background, or the CMB. So this CMB is this afterglow of the Big Bang, only 300,000 years after the Big Bang. It's the earliest stage of the universe that we can actually observe and see. So instruments like the Planck satellite have mapped the structure of the CMB very carefully. And what we can see are these hot spots and cold spots in the CMB that correspond to regions in space at the time that it happened, 300,000 years after the Big Bang, where the universe was denser or less dense. So basically, the hot spots correspond to regions where the universe was denser, and the cold spots to regions where it's less dense. So by mapping the CMB, we can learn how matter was distributed in the early universe very, very early on, 300,000 years after the Big Bang. And so once we learn how the matter was distributed at that time, and this is way before there were stars or galaxies or clusters or anything like that, the universe was just a soup of dark matter and hydrogen atoms, and well, there weren't even atoms before that, there were ions. So once we learn about the distribution of matter, we can put it in our computer simulations like this one. So start the computer simulation, distribute these particles of dark matter everywhere according to whatever we observe in the CMB, and then just evolve time forward and see how our universe managed to form these beautiful structures of galaxies and clusters of galaxies from that initial condition of this dark matter soup that was everywhere. So what you see in these simulations is just dark matter that through its gravity just like collapses to form these beautiful structures, filamentary structures that you see. And at the centers, these focal points, we call them dark matter halos. These are the locations where dark matter really forms these bound structures where the density really goes up. Now, in the 1980s, there was a new theory for the formation of galaxies in our universe that said, as dark matter collapses to form these dark matter halos, with itself, it pulls normal matter, like helium and hydrogen. It pulls them at the center of these dark matter halos, and that's where galaxies are formed. So look at a dark matter halo, and at the center of it, you will find a galaxy. So bigger dark matter halos should form bigger galaxies, and smaller dark matter halos, like this one, should form smaller galaxies in them. So there is the absolutely crucial link, that there's a link between dark matter halos that is basically the glue, the gravitational glue, and normal matter like hydrogen and helium that form our stars and our galaxies. And so these normal matter, like galaxies, they sit at the center of these things.
Before you can play with just distributing that dark matter and see how it reacts with itself, you effectively cast it on a table, a three-dimensional table, but a table nonetheless. Do you have to make some assumption about the topology of the universe? What kind of a shape?
Yeah, absolutely.
Do you assume it goes on infinitely, or do you assume it's spherical?
Yeah.
What do you assume?
Yes, you're absolutely. That's a great question. You do have to make a lot of assumptions about the cosmology and how the expansion of the universe, for example. And so we have very good constraints on these things. So we have very good numbers that come from different experiments. There's different measurements using, for example, the same thing like the cosmic microwave background, or from observing supernovae in our, in the earlier universe. So we have very good constraints that we understand how, the expansion history of the universe and its geometry, like you said, its topology. And so these simulations, they include that. And they also include, the variations, because there's some uncertainty on some of these levels. So they include those things. But you're absolutely right, yeah.
What topology do you assume? Flat? Hyper?
Yeah, so currently, as far as we know, the universe is flat. Yeah, and it was a big discovery, more than 10 years ago. We didn't know that the universe was flat. But currently, as far as we know, the universe is flat, yeah.
And you assume it goes on and on and on?
So in a flat universe, that would be the implication.
Like Euclidean geometry?
To a high degree, yes, yeah. I can't say exactly Euclidean because we live in a world of general relativity. But to a first degree, it would be like a flat, Euclidean geometry, except that it's an expanding universe too at the same time. So one of the fascinating things about these simulations and dark matter is that now we can go and compare the predictions of these computer simulations and models with actual data. So we can compare a lot of different things. If I go to the next one, we can study what are the predictions for the number of galaxies, for their masses, their distribution in masses. How many more massive galaxies, how many less massive galaxies do we have? What is the distribution in the size of galaxies? What about their distances, how they're clustered together? And every one of these questions that we have asked, there seems to be an almost perfect match between the predictions of these cold dark matter simulations and actual detailed observations that we have. So there's a lot of different observations going on. People look at a lot of different observables and they compare them with these simulations. And as far as we know, everything seems to be bang on. And that has convinced most astrophysicists that the cold dark matter has to be the correct description for dark matter. I mean, how else could it predict so many things so beautifully about our universe with such simple assumptions, right? So at this point, what we're waiting for is just for somebody to come and detect dark matter in a lab on Earth and win the Nobel Prize, and that's the end of it. That would be nice. So there are some experiments. One of them, the AMS on board the International Space Station. There are other experiments deep underground in abandoned mines, like the Lux experiment. And so these are trying, very serious people are trying to detect dark matter, by various techniques. How, for example, it would just collide with some atom in a particular direction, and from that collision you would see a kick. They're very, very sophisticated experiments, but so far we haven't had a signal. So far we haven't had a detection. And in the next few years and decades, there's going to be a lot of progress in that. But while waiting for that and not detecting dark matter here on the Earth, us astronomers, we try to learn more about it, a little bit more in the sky, so from astrophysical phenomena. Now, in the early 2000s, we started noticing as computers got more powerful, so we started having higher and higher resolution simulations like this one. And we started noticing a very unique and extraordinary prediction of the cold dark matter model, which was that halos, dark matter halos of typical normal-sized galaxies like the Milky Way were composed of tens of thousands of smaller tiny clumps like this one that you see. So this is a simulation. It's called the Viola Co2 Simulation. So the idea here is that this is a simulation of the dark matter halo of the Milky Way. So you can imagine this is all dark matter, whatever you see, but the Milky Way, the galaxy, and our disk, everything would be sitting somewhere at the center of this. So all this dark matter is basically the birthplace of our galaxy that just pulled all the material through its gravity. But if you remember, we said that every one of these dark matter subhalos was predicted to form its own mini galaxy too. So if it's predicted that our galaxy has tens of thousands of these dwarfs dark matter subhalo, and each one of them has a galaxy, so we should expect to see tens of thousands of dwarf satellite galaxies for the Milky Way. So just look around our galaxy, it should be filled with tiny, tiny dwarfs all over us. Now, for a few decades, a lot of very deep searches in the sky have revealed only about 50 galaxies. And that's where the controversy begins. So it's called the missing satellite problem. Dark matter halos, the cold dark matter is predicting tens of thousands of them. We see only 50 of them, and what's going on? This is the first place, or one of the most important places, where we see this discrepancy in the predictions of cold dark matter and what we see. So I'm going to cut to the chase and tell you what the solutions are and what we think about it. So there are two solutions here. One is that this description is actually correct. Maybe cold dark matter is the true description of dark matter. Maybe there are, our galaxy has a lot of dark matter subhalos all around it that are going around us. But perhaps we just don't see them because they don't have galaxies or stars in them. So the flaw is not in the theory of dark matter, but in the theory of how stars and galaxies form in dark matter halos. And that's the theory of galaxy formation. But alternatively, you can imagine that perhaps, we're just, chasing the wrong thing, and dark matter is, are smooth like this one on the right. And they don't have any dark matter subhalos. We don't see them not only because they don't have stars, because they don't exist at all. So there are alternative models for cold dark matter called warm dark matter, like the one on the right, where you have a different particle property for that fundamental particle that that is dark matter. And so by learning something about the structure of dark matter halos, we can learn something fundamental about this particle, some fundamental physics about its properties and what it is. And that's why this is very exciting, to try to learn if dark matter halos are like the one on the left or the one on the right. So this is just a little simulation to show you why we call them cold and dark warm matter. So one of the cups here has cold water, the other one has hot water in it. And we just put a few drops of ink in both of them. And as you might expect, the one on the right, which has hotter temperature, the ink starts dispersing much faster, so this structure in it starts to dissolve and become smoother much more quickly. than the one on the left. So when we say warm dark matter, just imagine that in warm dark matter, every one of these warm particles has a lot of energy. So it just goes around really fast, and it doesn't allow small structures to form. And because of that, it becomes smoothed out like this one, whereas the cold one still clumps together and stays very clumpy. So quick recap. So our best favorite model of dark matter is the cold dark matter, but it predicts tens of thousands of dwarf subhalos around our Milky Way. If the assumption is that each one of them should have a galaxy inside it, we should expect tens of thousands of satellite galaxies around us. But in reality, we only know of 50. We have spent a lot of time looking for them, and we don't find them. So solution, again, it's either cold dark matter, what it is, but we need to revise our understanding of how the smallest galaxies form in these dark matter halos. Or perhaps they don't exist at all, in which case it points us to a new theory of what the dark matter particle is, and we learn something fundamental about the nature of dark matter, and that would be really exciting. So all we need to do is to be able to measure the structure of dark matter halos. Is it the one on the left or the one on the right, and we're done with it, and that would be absolutely great. And you might have guessed at this point, we are trying to do that with gravitational lensing. Now, the key idea that you want to use here is that you don't want to look at anything, because dark matter, as we know, doesn't emit light, it doesn't show anything. So we want to use something that is purely gravitational. So that's why we use gravitational lensing. Remember, the bending of light in the background galaxy is being done because of the gravity of the middle galaxy. And so it is imaginable if that middle galaxy had a lot of structure in it, like clumps, those clumps would distort the image of the background galaxy. And so through these tiny, subtle distortions, we can learn about how clumpy this middle galaxy is. It's a little bit like looking at frosted glass like this one. If you look at an image, background image, like the one on the left, you know that the glass is probably pretty smooth. And it doesn't have any, wrinkles or ripples or anything in it. But if you look at this image here, because of the distortions in the image, you know that the glass itself, is frosted and it has like tiny fluctuations on it. Or if you look at the middle one, you know that yes, but these fluctuations are larger scales. So by looking at the distortion of the background thing, not only do we know that there is like something, but we can actually map out its granularity and learn something about how it's constructed there. Another example is the same old example of wine glass that we saw earlier. So if you have the wine glass and it's lensing the image of the candle like that, if there was a little water droplet on the foot of this, then that water itself adds another layer of lensing. So even if we can't see the water itself because it doesn't emit or doesn't have any colors or anything, we can still know it's there because you can see that it breaks that image into two different images. So just by looking at the distortion in the image of the background thing, we know that there is a little droplet there. And that's how we try to find these tiny dwarf subhalos. So here's a simulation showing the effect in gravitational lensing. So the only thing that you have to notice is that in this case, the effect is really, really subtle. The kind of effect that we were trying to look at is barely visible to the naked eye, even in these simulations. Here's an image of a background galaxy. It's not even lensed. So this is a computer simulation. We just bring these lensing galaxies in front of it, and now you can see that it's being lensed. So the images are distorted. And then we add a tiny subhalo in this location, and we add it and remove it a couple of times. Now, and so you can see there's a little kink into the arc here, right? So that little kink in the arc is what we were trying to find. And so the more massive that subhalo is, and now we don't even show it anymore, but you know when it's there, when the arc starts just bending around. So through these kind of distortions, we try to find these evasive dark matter subhalos and count them up, basically, figure out how many of them there are and if they are there at all or not. So we had some data on these sources, so you might ask, so why couldn't we just do it quickly and move on with our lives? But it's a difficult thing to do. So look at these two images. One of them, so both of these are computer simulations. One of them has a dark matter subhalo in it, and the other one doesn't. And just putting them side by side, looking at them, you can't even say if there's any difference between the two of them. But once we put them on top of each other and we start blinking between them, now you notice that there's a little kink here. There's a little change in the brightness of this thing that comes when there is a dark matter subhalo. So there's a very, very subtle effect that we're trying to find. And because of that, we need really, really high resolution images. We need very, very good quality images with a lot of signal We also need very powerful image analysis techniques. There could be lots of things that could confuse us, that could be something like that, but we need to just, ignore and really try to find a signal that is unique to being gravitational lensed by a tiny subhalo. So while waiting for that kind of high quality data, I spent a few years just writing these image analysis techniques that basically get these sort of images or ALMA data and measure their subhalo populations. And if you remember, for ALMA, we said that we can move the antennas around. So you can just put them close together, and then you have a lot of sensitivity but lower resolution, or you can put them really far apart. Look in this image. These circles are different antennas, and they're really far apart from each other. So this is in the extended configuration. They could be, if you remember, 10 miles apart. And so finally, when ALMA went to that configuration about 2 years ago, and we got the very first data on a gravitational lens with that quality, it was absolutely amazing. So this is the image that we saw. So what you see in blue is from the Hubble Space Telescope. You can see individual pixels. And then what you see here is what ALMA sees, the background lens galaxy with all this beautiful structure in it. And it's absolutely fascinating. So as soon as we got this data, we knew that this is the kind of data that we've been waiting for to see if this level of quality in the image is sufficient enough for us to find dark matter halos or not. So we started working on it, and soon we realized it's very difficult. You need really a lot of computational power because the kind of image analysis that we were doing computationally is very expensive. So we had to go to some of the biggest supercomputers, and you had to use 4,000 computers, 4,000 cores for about 6 weeks just to do the one analysis. And once we did it, but the result was absolutely amazing. So we found that there was a dark matter subhalo at the location where you see here. So again, we don't see it. We only know that it's there because of the kind of distortion that it's causing on the image. But we could find this with a very high significance, and that was truly amazing. So this is the only science plot that I'm showing. I'm trying not to show it anything. So this is from that paper. What you see here is basically the mass of these dark matter subhalos that we're searching for. So it goes from 10 million solar masses to 1 billion solar mass. And on the y-axis, we're plotting their abundance. How many of them, their density basically, how many of them are you expecting to see here? And so the gray band here is the prediction of the cold dark matter model, and the error bars are measurements in this one system. And so far in this one system, it seems that whatever we expected with this one detection and the rest of non-detections. Now also remember, when we don't detect them, also we learn something about them, right? Because it's gravitational lensing. Just like the glass with the sailboat that you see on the background, when the image of the sailboat is just not distorted, you also know that the glass probably doesn't have any fluctuations on it. So here too, we can also place constraints and say there's probably not that many of dark matter subhalos of, for example, that particular mass because we don't see them here. So we can combine these to these kind of things. But just like, polling for an election, you don't want to call one person and just ask them their opinion. You won't know which way the election is going. You want to call a lot of people. So here we also want to call a lot of gravitational lenses to build up really good statistics about this. So in the next few years, we're planning to look at a lot of these gravitational lenses and to study them with high resolution with ALMA. In fact, this year, right now, ALMA is busy observing 3 of our sources at unprecedented quality, and I'm really excited to see that data that we haven't received yet. So that's going to be the plan for the long term. What's exciting is that we have a lot of targets, a lot of gravitational lenses that we discovered with the South Pole Telescope. ALMA is working great. Now, the only thing at the end that I'm going to mention is our recent work in how to study these things. You remember, it's really difficult, so we had to put it on 4,000 computer cores to study them for so long. This brings us to artificial intelligence. So, for all of us living around the Bay Area, it's hard not to appreciate all the amazing things artificial intelligence is doing these days. We used to live in Mountain View, and every day bump into a Google self-driving car. Drives way better than me. And Skype now translates for us, right? You can just talk to somebody and Skype live translates, and there's nobody sitting there and listening and typing for you. It's actually the computer doing it. How amazing is that? And most amazing of all, I don't know if you guys know about the game of Go, but computers last year managed to beat the world champion, the European champion of the game of Go, which is absolutely amazing given how complex this game is. And so computers can now outperform humans in a lot of things. So the question, I guess, it's not an exaggeration to really say that artificial intelligence is really going to change a lot of things or everything. So the question is that, can we use it for gravitational lensing? Could we give some of these lensed background galaxies and have computers with much more intelligent techniques analyze them for us and make it simpler? So that brings us to machine learning, which is a branch of this artificial intelligence. And as the name suggests, it's machines learning. And so if you go to Wikipedia, and I can read it, machine learning is basically a branch of AI that is the study of computer algorithms that improve automatically through experience. So what they do is that they just look at data, and you don't tell them, you don't program them specifically what to do. You just show them the data, you show them the true answers, and they just figure out what to do themselves. So one example of machine learning is if you have a MacBook Pro, just open your Photos app, you'll go to people, and it just shows the different images that you have, people in your images, and you can classify them. And that's Cillian, 2 months, and he already knows everything about him, right? And I'm amazed because he's been changing really rapidly, right, in these 2 months. But my laptop already knows who he is and puts all their images together. Even though it's pretty fascinating, some of these are very difficult. This one, half of his face is covered by the pacifier. And my laptop automatically knows who he is. And this seems like a much harder problem than the problem of gravitational lenses with me. If I wanted to just write a simple algorithm how to do this, it would be impossible. How do you define a person? So the way we do that is using artificial neural networks. And so artificial neural networks are basically computational structures that are modeled after the human brain, or basically the brain of living organisms. So they have these neurons, so they pass the data on one side, on the left side here, and different data basically activate different neurons, and they take different paths, and they come on the other side. And so your result is, on the end side, whatever that you want, on the right side. So just as humans, babies learn by seeing new examples. You show them an example, and you say what it is, and then they just make the connection. Neural networks, they too learn by just being shown examples. One example is, how can a computer read handwritten numbers? So we just show them a number, 5. It could be this 5, it could be that 5. And we want the computer to know what a 5 is. And this is a very difficult problem if you're just doing computer programming like before, a deterministic program where you just write and you say, look at this pixel, look at that pixel, and make a decision. But with neural networks, what you do is that you just give this data to the computer, and you give it the true answers too, and you put it through something called multi-layer perceptron or neural net. And this is a video that I found online. It's absolutely, I love it. It's amazing. So you put the different numbers on one side of this neural net, and it goes through different layers. And on the end side, you just tell it what the answer is. So you say, oh, that's a 2, that's a 3, that's a 4. And the neural network will figure out what connections to activate to map these two things together. And then after some time, it figures out, oh, this is a 2. So all the 2s should go through this route. So now you put a new 2, and it knows the answer, or a 3, or something like that. So we're trying to do the same thing with neural networks, with gravitational lenses, where on the one side, we will just give it what we observe with with our telescopes, and on the other side, we want to learn about the properties of dark matter and how it's distributed and things like that. And this is an ongoing work, and so we're hoping in the next few years this could simplify a lot of our things and speed up our calculations. So given with the number of large sources that we have, and the new techniques, and the high resolution of ALMA, we hope that we can answer something about the properties of dark matter. I'm going to stop there. Thank you very much. Yes, please.
Everyone assumes that the dark matter is made out of particles. What kind of particles, God knows, but particles. And I wonder if there is some quantum mechanical argument to show that they should be made of particles. Why could they not be made like matter was thought to be before it was atomized? In other words, matter would be continuously
A field.
divisible, and
Yeah.
there would be no smallest particle of it.
There are lots of different theories. So dark matter part, like the cold dark matter, is by far the most accepted theory. It is not the only theory. There are a lot of alternative theories. There are theories that dark matter would be just a field like what you mentioned. There are other theories that would the alternative is that there's no such a thing as dark matter, and it's a modification to gravity. So modified gravity is, and so there are competing ideas out there, and I am absolutely not in a place to comment on them, to say what they are. I can only tell you that based on the consensus in astronomy, most people think that that dark matter is probably made of cold dark matter, that of particles because of a lot of reasons. But I don't know the details of all these other theories. Yes.
Well, just focusing on lensing and galaxy formation, I'm sure I have this wrong, but it's my understanding that it's something like 4% of the galaxy, of the universe rather, is what we see, and dark energy is maybe 30-something or 40-something percent. Dark matter is another 50, 60-something percent. I don't think I heard you discuss dark energy.
Right.
How would that possibly come into play with regard to either lensing or galaxy formation?
Yeah, excellent question. So first, the energy content of our universe, something about 70% of it is dark energy, something 25% of it is dark matter, and the other 5% regular matter. But that's on the large scales. So dark energy is a very different and fascinating topic, and it does influence the expansion of the universe dramatically, and that's how we know about it. And it does have a considerable effect on other lensing measurements like weak lensing. So weak lensing is basically the minute stretching of the galaxies because of the same effect, because of gravity, but it's not strong enough to produce multiple images like that. It just makes everything just a little bit stretched. And so there's a lot of weak lensing surveys, and so things like dark energy play a major role because dark energy affects the universe on very large scales. What we're looking at here is like a tiny pencil beam, that we're looking at, a very local effect around very high density regions like galaxies. And so dark energy doesn't influence our observations so much on these small scales, yeah. Yeah, thank you for the question. Yes?
Do you have any plans to use the motion of the Earth in its orbit to extend your baseline to get higher resolution?
So you need to do the observations at the same time. That's one key. So so we cannot observe them now and then go 6 months from now on the other side and make measurements and combine them together. They have to be at the same time. The key idea here is that the wave front that is coming to us. So you can imagine that if I have two telescopes that are sitting like this and there's a star there and its light is coming to us, it first reaches the first antenna and then it reaches the second antenna. And because it's a wave, by the difference of the distance that it traveled, we can know something about its phase and where it's coming from. And that's how this technique works. Yeah. But there's something else that you might find fascinating. It's basically very long baseline interferometry, where we have telescopes that are really, really far apart. So we could have telescopes, the South Pole telescope, and another telescope, in Chile, another telescope in North America. And so they would observe at the same time, but they don't combine their data at the same time. So they just record their data, and then later they're combined. So VLBI. And that's really powerful. You can get extremely high resolution. But the trade-off is that once you get these very, very sharp images, on the other hand, you lose sensitivity. And that's the catch. That's why we don't do it all the time. That's why we move the telescopes. Then you need extremely bright things to look at. Because if they're not bright, basically it'll be just noise. Yeah. Thank you for the question. Yeah. Yes?
Although dark matter is shown in a number of satellite galaxies, does it help explain the formation of all the globular clusters around galaxies?
Sorry, can you repeat the question again? Could dark matter explain the formation of globular clusters? Is that? I don't know. I don't think so. In fact, globular clusters they don't have dark matter that we know of. And that is the thing that, we've established that differentiates galaxies from any other collection of stars. So I think my favorite definition of what a galaxy is that it is something that has basically a collapsed dark matter. And so when we look at globular clusters and their motion of stars in them, and we map their dynamics, it's very clear that they don't have any dark matter. And I think, the formation of globular clusters itself is a huge mystery, as far as I know. I'm not an expert in that. But we do see dwarf satellites that have much fewer stars than globular clusters. We have, satellite galaxies around the Milky Way that only have, a few thousand stars, a few hundred stars. And even then, we just look at the motion of these stars in these like tiny, tiny dwarf galaxies, and they're just going way too fast. So you know that there is a dark matter clump there, which is absolutely fascinating, yeah. Yes?
So why aren't there more satellite galaxies then? And does it have to be warm or cold? Can it be, is there any way it could be both in different conditions?
So what was your first question?
Why aren't there more satellite galaxies then?
Yeah, that's what we don't know. So that's what we're trying to find out. So our hypothesis here is that there is either not that many of them because dark matter is smooth and it doesn't form those dark matter halos, and as a result of that, no galaxies form inside them. Or maybe dark matter is cold, so there is a lot of these dark matter halos, but they just don't form galaxies inside them. And the reason for that could have something to do because the process of galaxy formation is very messy. So you have to understand a lot of thermodynamics, gas heating, shocking, adiabatic cooling, and a lot of different processes. And so we try to understand some of those things, but it's messy. It's like weather prediction. You can have some understanding, but it's a very complex phenomenon. So if we have cold dark matter, and these dark matter subhalos are actually there, why stars don't form inside them has to do with a lot of this messy physics, and people they have hypotheses for some of these things. For example, one of the most important things has to do with supernova. So the idea is that supernovae at the birth of these tiny galaxies, they output so much energy in the first generation of stars that it basically kicks out all the gas that they have. And so, if you just wipe out all the gas that they have nothing else left to form more stars there. And the gas gets, kicked out because they don't have much gravity. Whereas, in the Milky Way, in a massive dark matter halo, there's so much gravity that no matter how many, supernovae you have, it will still, keep the gas together. And your question about cold dark matter, warm dark matter, these are, basically warm dark matter is, any dark matter with some finite temperature. And so that temperature is something that we try to measure. And whereas cold dark matter is basically referring to that kind of like ideal case where that temperature is so small that, as far as observationally we're concerned, it's, we cannot measure it. Other questions? All right. Thank you very much. Thank you.